CFSAN stands for Center for Food Safety and Applied Nutrition, so I work for like the F and FDA. There are 5 centers. For example, CEDAR is a Center for Drug Evaluation Research, and there are other centers. And I work at a division of CFSAN called the Division of Food Processing and Science Technology, and that's in Bedford Park, Illinois, about maybe 15 miles south of here. And our facility is actually at, the campus is called the Moffett Campus. Let me go back. And the building is owned by the Illinois Institute of Technology. So we collaborate with IIT and food science research, and the institute's called this IFISH for short. And there are also members from industry belong the food companies, and we meet occasionally to and collaborate on some projects, and food process safety, nutrition, and national security related to food. It's about, right now, 60 scientists, about 40 FDA scientists, and maybe 20 IIT. Most of them are microbiologists. We do mainly microbiology research, but we have some pretty strong chemistry program too. And we also have graduate program. There's about 100 master's students studying food safety and food process engineering, and a lot of the students work with FDA scientists too on their projects. So here's some of the food chemistry projects we've worked on in the last maybe 10, 15 years. My first project when I came in 2003 was analyzing French fries, mainly for acrylamide, coffee, toast. And I just saw in the news in California there's going to be a cancer warning for coffee because printed on the cups because of acrylamide. So I would say I'm not afraid to drink coffee, but I would not eat the dark roasted beans. So, and so we did a variety of work and a lot of different projects in food adulteration and mitigation and control, working on a heavy metal contamination project with filtration of actually beer and wine now with a diatomaceous earth filter product. So that's pretty interesting. And we also do a lot of research at the Moffett Center on packaging, food packaging, seal integrity, migration, nanomaterials release. That's actually my main project now, is working on nano formulated food packaging and migration of nanoparticles out into food simulants. So it's something different for me, which is interesting. And so that's sort of the overview of the kind of food chemistry research done at IFISH. And I'd like to go back in time now to sort of go into the history of FDA a little bit. I find it pretty interesting. I just took this picture from FDA, some history office of a lab back in 1907. The Bureau of Chemistry was the predecessor to the FDA. And it's amazing how clean that lab looks. I just wonder if those, they spend all week cleaning and getting dressed up, or the lab always looks like that. I don't know. I imagine they probably clean up just like, we do today. And in fact, the Bureau of Chemistry was created in 1862. Abraham Lincoln appointed Charles Wetherell, the first chemist at new Department of Agriculture. And the very first project was a food adulteration project on study of grape juice and winemaking, dealing with whether adding sugar to increase the alcohol content would constitute adulteration. It's concluded the practice was legitimate. But 46 years later, when in 1906, the actual first food laws in the country came out in the Food and Drug Act, court ruled to the contrary. Cider made harder by adding sugar was found adulterated. So some things change, but they stay the same. The scientists get the data, show the facts, and then the lawmakers and the courts decide what to do with it, and it can change. So I found that pretty interesting. So anyway, this book, Some Forms of Food Adulteration, Simple Methods for Their Detection, came out in 1906. You see Harvey Wiley's name at the top. I imagine a lot of people have heard of Harvey Wiley, sort of the father of the FDA. And this is our CFSAN headquarters is in College Park, Maryland there. That probably about 1,000 FDA workers there, probably about half of them scientists. So, and they have very nice lab. They have very good, chromatography equipment there. I've been there a few times. So I had to copy one of the methods out from the 1906 book to see what the science was like back then. Detection of formaldehyde. Detect formaldehyde in milk, add 3 or 4 teaspoons of the sample are placed in a teacup with an equal amount of strong hydrochloric acid and a piece of ferric aluminum about large as a pinhead. And liquids being mixed by gentle rotary motion. And at the end of this time, formaldehyde be present, the mixture will be distinctly purple. So back in 1906, there was a lot of work being done on food adulteration, but I really was impressed with the safety and the environmental concerns that they had with the sample, that the hydrochloric acid is strongly corrosive, must not come in contact with flesh or clothes. The operator, it must be diluted greatly with water before it was poured into the sink. So anyway, so it was safety rules were a little bit different back then. But here's just a few more milestones of history and food regulation. And the 1927 is really when the term FDA was first being used. The Bureau of Chemistry was separated into the 2 entities. The Food, Drug, Insecticide Administration was one of them. And shortly after that, it became the Food and Drug Administration, and then the term FDA came into being. So, and you can look up if you're interested, just go to the FDA website, fda.gov, and you can start poking around and find all kinds of interesting stuff about history of the FDA. But anyhow, on to modern times. Well, this one is the section from the Food Code, FD&C, that describes actually what food adulteration is. And there are a couple different definitions. The one we'll kind of be focused on is number 4, if a substance has been added there to a mixed pack to increase its bulk or weight or reduce quality or strength, make it appear better, greater value than it is, economically motivated adulteration. It's a crime, can be punished by fines or jail, and we might even show an example later on where somebody went to jail for that, so we'll see. So it is adulterating food is a crime. It's in the federal code. And I think the one incident that brought adulteration into everyone's mind back in 2008 was the melamine incident. Probably everybody in this room has heard about that. Some babies died in China. And I know in the U.S. it got into the pet food. A lot of pets died and got sick. And so I think this is the first time that food adulteration got into the public consciousness big time. And so it kind of brings us to what was going on now. And I looked this morning before I came to see how many research projects CFSAN has going on now. It's almost 400. About half of those are chemistry, and a lot of them involve food adulteration. So I had to pick a few to be able to go into some detail. And show some of the work we did in our labs at IFISH and some that's been done at some of the other FDA labs. So adulteration of skim milk powder with plant proteins using UPLC UV. That was done in my lab about 5 or 6 years ago. We'll look into that one. Adulteration of lemon juice with water and citric acid with UPLC high-res accurate mass spec. We'll look at that a little bit. And adulteration of orange juice and milk with model compounds using UPLC high-res accurate mass spec. That was done at College Park, that work, at our headquarters. And then I think there'll be enough time. I want to go into one that was investigated by the ORA, Office of Regulatory Affairs, and that's the part of FDA that can put people in jail. So they do the more exciting stuff. And so anyhow, go on to the first example, non-targeted detection adulteration, skim milk powder with foreign proteins using UPLC UV, and this is the only, well, this one we didn't use any mass spec, just UV detection, collaborating with Jeff Moore, USP, and Jim Harnley from USDA. This is a part of a real big project the USP managed to look at all kinds of different techniques, NMR, UPLC, mass spec, different chemical techniques for detecting adulteration of skim milk powder. So we worked on the UPLC UV, and skim milk powder was considered a good model food product to detect adulteration because it's such a high volume product and found in many different kinds of foods, and about the only real standard of identity is the minimum protein standard. And the idea was with this whole project that to go into a non-targeted mode, which means you don't really know what you're looking for. You're looking for differences in a suspect sample versus the good stuff. So USP has pretty formal definitions now for targeted and non-targeted. I don't have them up here, but we'll go into that as we go on. And so what we wanted to do with this UPLC UV method with the skim milk powder is come up with a very simple sample prep to just basically dissolve the sample, just get sort of a chromatogram profile, not necessarily separating all the peaks, and we don't have standards. We didn't inject standards of the various milk proteins. So in my mind, it was basically treating a chromatogram like a spectrum. And we wanted to see if in a suspect sample, an adulterated sample, does the fingerprints match the authentic skim milk powder? Can you tell it's deviating? And the thing with this, we were talking with Natasha before, with a non-targeted approach to anything means you don't really have standards. You don't know what you're looking for, but your model of the good stuff has to be really broad and comprehensive. You really have to know what the good stuff is to tell that you have something that's not good, and that isn't always easy. So how do we do this? Well, we just did a very simple shake and shoot, really. You don't want a lot of sample handling to lose possible contaminants or adulterants. Use a denaturing buffer with, I think, 6 molar guanidine hydrochloride, a chaotropic agent. Then diluted the sample some more, centrifuged to get out any particulates. And then we ran this on the acuity system with a C4 protein column, pretty standard conditions, acetonitrile, TFA gradient, 0.2 mLs a minute, 50 degrees. It was a pretty long run time, which sort of worked against this method, but we monitored the wavelength 215, 285 points per second. And this is crucial in doing fingerprinting because essentially your chromatogram is like a spectrum, like the wavelengths have to be right on every time, and the peak retention has to be right on every time. The way we're treating this statistically, you can't have like a window and have your peak, in the window, because you're not doing that. And so that pretty good reproducibility in the same day. And then looking at injection, the top trace is 100% skim milk powder, and the bottom trace is 100% soy. As you look at the 10%, the second trace from the bottom, you can see some of the soy peaks appearing in the SMP chromatogram, and maybe even at the 3% level you can see. But once you get below 3, you really can't visually see it all that well. So you have to use a statistical mathematical treatment anyway, even with 10%, to say it's adulterated or it isn't. So in what I found out, because I'm really not a protein chromatographer, it's my first time chromatographing intact proteins, is that, and that just shows you where the soy peaks appear. So you can see there are some perturbations of the skim milk powder profile. So it's pretty easy to see at 10%. Well, if we look at samples injected on different days of the skim milk powder, now we can start to see some drift. So one thing I learned off the bat doing proteins is that you can see a lot more retention time drift if your column is not equilibrated or somehow contaminated or whatever. And that's just unacceptable when you're doing the fingerprinting approach for detection. So we use magic here on this, which is alignment of the chromatograms. And now I find really that almost all the data systems have these alignment, chromatographic alignment features built in. We used Lineup here, which is from Infometrics and their chemometric software, to actually realign the chromatogram. So you pick a target, you say this is my good chromatogram. You can then you pick your samples to align, and this correlation optimized warping, I don't want to get into this. It basically breaks the chromatogram in different segments and lines each of the segments up with like a correlation coefficient. Anyway, the upshot of it all is, if the blue is your target, in this case the red is the unaligned, and after the alignment software, it aligns right up. And this alignment shows up in other chemometric approaches where you have to have the retention times right on the money to get meaningful results. So there are 14 pure SMP chromatograms lined up. This is the Pirouette chemometric software. They lined up pretty good. And actually the hardest part of dealing with all this was getting the data out of MassLynx into Pirouette, because you're dealing with huge data files here, 9,600 time points, and then the UV intensity at each time point. We had 87 samples in the set, so there's over 800,000 data points there. And once we had the data in MassLynx, it's exported into ASCII, then put into Excel, and then the chemometric software could read it. So just moving these big data sets around took a lot out of me. But here's looking in the Pirouette line plot view, essentially, at one pure SMP and then the adulterated with the soy. It's pretty easy to see with one pure sample and adulterated it differences. But when you're looking at maybe hundreds of varieties of different pure material, you have to have that, you'll see some variation. It's not as easy to see. and you have to have a mathematical treatment. So one treatment we used was a univariate treatment, which is essentially point by point looking along the chromatogram and seeing and coming up with confidence limits of the good chromatogram and saying how many points are above or below that confidence limit. So, and you choose different thresholds, number of points, and so forth. And this is sort of what it looks like. I don't know how well you can see that, but the mean minus the 3 standard deviations and the mean plus the 3 standard deviations are sort of the confidence limits around the whole sample of all of the good skim milk powder. And then the different colors are the adulterated, and you can see clearly like some of the colors where it goes above and outside the confidence limits would be adulterated. And it works, it's like I say, it's easy to see with 10% added, but when you go to the lower levels of adulteration, it didn't really work out so well. So just looking at some of the classifications using the low threshold, 25, and the high of 200, well, 10%, all of the adulterated samples, all 8 were classified as adulterated, and both thresholds, and at 3%, which is sort of what we thought we would get. But where you get below where you really can't see, and you have to rely on those confidence intervals and the thresholds, it sort of falls apart. So even at 1% of soy, only 5 of the adulterateds were classified correctly, and 3 were classified as non-adulterated. Now with a 200-point, none of them were classified correctly. And then you have to worry about false positives. So the pure SMP, which should have 0 adulterated, you start to see some adulterated come in as you go to the lower threshold. So the point-by-point approach didn't really work all that well. So we tried some chemometric approaches, and do most people in here do chemometrics or know anything about it? I don't know. I didn't really know much about chemometrics till I started working on this, but this project. But if you're interested in learning chemometrics, I sort of was self-taught. The Pirouette, and I imagine the other softwares, will let you download their software for free on your own computer and use sample data sets to learn how to run the software. You just can't put your own data in. So that's sort of what I did here, just in case anyone's really kind of interested. So we did some PCA, principal component analysis. I think most people have probably heard about that. And we did some feature selection. That's the big buzzword you're going to hear over and over. Rather than use the whole chromatogram, you pick areas, you pick something that'll really allow you to see small differences. And this work was done in Solo, that's a different chemometrics program, by Jim Harnley. And by picking this one narrow region from 5100 to 5500, that's the data point number, not the time. He was able to separate the, at least on this plot here, whoops, wrong one, the 10%, the little stars from the red pure SMP, the 3% pretty easily, and even the 1% started to separate out here when we used feature selection. But it was decided after we got this far, and this was a lot of work, that this was just too time-consuming. And even though it was sort of working, a lot of the other techniques like near-infrared and amino acid fingerprinting, which is UPLC, was working a lot better. So we kind of dropped this. But it just shows you what you can do, different approaches using a chromatogram as a fingerprint in a non-targeted way. And so it was a challenging method. It was too long, really, for what we wanted. The data handling was kind of complex. And so we really didn't do too much more with that. So we'll move on to lemon juice. So juice has been something like been adulterated forever. And this is a letter, I don't know if you can read it, but it's from the National Consumers League to Margaret Hamburg, who was the FDA commissioner, 2012. And the Consumers League was complaining that lemon juice is being, imported lemon juice, adulterated to very high amounts, like 90% adulterated. And they wanted her to do something about it. So the only specs that are in the federal code for lemon juice are acidity and Brix. So you need the acidity. Essentially, you could have water with that acidity, 4.5, and a Brix of 6%, and you could theoretically call it lemon juice. So, and the reason that the letter got written is because the importers and the Consumers League hired Eurofins, it's a pretty big contract lab, did an extensive study. They did a tremendous amount of work on some of the imported samples. I'll get into that a little bit later here in a minute, but just the economics of it. Oops. So this is a few years old, but bulk lemon juice concentrate about 3,500 a ton. If you dilute it 50%, then add water, citrus acid, and sugar at these prices, you're essentially selling it at half price. So if you're claiming it's bottled 100% lemon juice, you make a pretty big profit on it. And Eurofins, getting back to Eurofins, I read some of these reports. They had like 30-page reports per sample. They did NMR, isotope ratio, pyrolysis, I think that was GC, the carbon-13 isotope ratio. They did like about 30 assays on each sample. So I'm imagining the cost per sample was many thousands of dollars, not something you're going to routinely do. So we were asked to sort of look at a simple screening method. And before that, okay, I get into this a little bit more. Carbon isotope ratio will detect adulterations because the amount of C13 in a C4 photosynthetic plant, which is like beet sugar, is different than in a citrus plant. And this technique, it's expensive, it's complicated, it's not routine, but it's considered the gold standard for this kind of adulteration detection isotope ratio. And anyhow, this is what the upshot of it was that these lemon juice samples were being diluted up to 90% and then called 100% lemon juice. And this is an import alert where basically FDA declared that these importers cannot import lemon juice until they've passed specs. So, and there's always import alerts out there and different things. And so what we did, we wanted to look for a simpler screening method, something that might be able to screen lemon juice quickly. So we decided to use UPLC, high-res accurate mass to look at the phenolic compound profiles and to see if we could use differences in the phenolic profiles to see if we could detect adulteration. And there's some problems. The phenolic compounds are not all that stable, and you had to work fast and you had to keep it simple again. So we used an Excella Exactive system. It's not the Q Exactive, sort of the base Exactive. We're just doing screening, looking at everything coming in there. And we prepared fresh lemon juice. We squeezed our own lemons, so we knew we had the good stuff. I made a lot of trips to Whole Foods and Jewel to buy lemons. And we used targeted and non-targeted here. We tried two approaches. And we had a young ORISE postdoc, Zhenfeng Wang, did this. She's now at the University of Maryland. We looked at total ion chromatograms and total mass spectrum. So I don't know if you can see that very well, but it's kind of small. We did reverse phase separation with formic acid and acetonitrile, standard stuff. And the top you can clearly see, again, with one lot of lemon juice in the green, 100%, then the peaks get smaller, the red 60 and the blue 30. But again, that's one lot, so, you know. And then she also did total mass spectrum, where basically over that run, about a 15-minute run, you just accumulate all the ions. And it's the mass spec equivalent of a total ion chromatogram. So we were going to use both data sets to sort of probe the samples. And we did negative mode because these are phenolics. Okay. And the two main phenolics we targeted are in lemons, areocitrin and asparagine. And then we measured the levels of those two compounds in the 22 lots of juice. And what you see there, top is areocitrin, the bottom is asparagine. The mean of all the content in all the lots is the dark line, and the two smaller lines is one standard deviation. So you can see there's a pretty big spread there, and that's just one standard deviation. And basically what it meant is you could not really use the phenolics as a marker because there's just such a high variation in the different lots. So in lot 17, you have 310 part per billion asparagine, dilute it in half, and you're still right in the middle of the good range. So there was just too much variability to target any of the phenolics for markers. So Zhenfeng also tried the chemometric approach here using PCA, and using the ticks separately and the total mass spectrum separately, she couldn't even separate the 30% juice that was 70% diluted from the 100%. So she tried combining both. She called it two-way data, so two sets of variables, the total chromatogram and the total mass spectrum, and actually got some reasonable separation from the 100% in the green and the 30% in the blue. And this is without any feature selection. No, this is everything. So we probably could have done better if we did some feature selection, but she had to leave and time was up, so this project kind of ended too. But 409 million variables. Again, you're getting into this big data thing when you get into this non-targeted thing. And I remember the first time she ran a computation on this, something like this, the computer ran for a week. She just put in her parameters, you know, samples, what we are looking for, the type of analysis, hit, you know, enter, and it ran for a week before we got results. So you get into this big data thing, and the data, I guess the data analysis really becomes the key part of this. So without feature selection, just using the whole chromatogram, it really didn't do, you know, all that well. So this is really what I want to go into, because this is the neat stuff. This is going on now, and this is work from College Park, out in College Park, Maryland. Ann Nohoff and Tim Crowley are the FDA people. They're getting help from Adulterant, Jerry Swigenbaum, because you need help with software. The software is so complicated that it takes a lot of training to get familiar. So what they want to do is just look for small molecule unknowns in some common food matrices. If you get a sample and someone says, what's in it? Is it adulterated? So they were going on non-targeted, and then they were going to try to identify what was different. So it requires powerful instrumentation, complex computation, and feature selection. So what they did, they used orange juice and infant formula, but they had 7 lots of the same, different lots of the same brand of OJ, 3 lots of the infant formula. They picked 1 lot from each food and spiked it with the compounds there, colchicine, hydrocodone, ricinin, yohimbine at from 10 to 100, 500 part per billion, and basically did a very simple method, the same thing, just shake, filter, and shoot, and run reverse phase, UPLC, high-res accurate mass spec, and let's see, it's essentially looking for a needle in a haystack. The key part here is that they're really focused on this paper is the workflow, because you're going to get really hundreds of thousands of ions. How do you decide what to look at? How do you decide what's meaningful? And so it really, you know, becomes an exercise in learning how to optimize the software. I mean, and I didn't want this to become a lecture on chemometrics and data analysis, but I know you guys know chromatography so well, but essentially this is what it ends up, you know, becoming. So let's see what they did. So they used Adulterant 1290 and the 6550 QTOF, reverse phase column, UPLC, typical, water acetonitrile gradient, and scan in the positive mode. Now they use blanks and a QC. The QC samples are spiked, with the adulterants, and I believe QC, and I think they might have used standards too, although I don't have that there, because they have to know they can find what they're looking for before they can say we can find stuff we're not looking for. So if our workflow works for things, small molecules that we know are there, it's got a good chance of working for other ones that we don't know are there. And in an actual non-targeted, you're not going to have those standards, obviously. So these data sets are really big. They had the lots of the orange juice, just looking at the orange juice, 6 lots of control, an adulterated lot, 5 reps, QCs, blanks. And so in a typical sample injection, they would have 10,000 plus features, which is defined as a compound by its mass, all the various peaks associated with that compound. And the files are huge, 2 to 3 gigabytes per file, easily. How do you mine that data to, get the information quickly? And what did they do? So data mining, I looked up data mining, discovering patterns in large data sets, involving methods at the intersection of machine learning, statistics, database system, intelligent methods applied to extract data patterns rather than looking at this chromatogram, this peak, this peak, this peak. You could spend the rest of your life on one data set. So here's sort of their workflow in a nutshell. This is really oversimplification. But the first step is to filter out noise. So basically setting a minimum ion count, say we're not going to, anything below 500 counts is noise. And then review the data files to make sure you're getting good, basic reproducibility. Binning, in this case, means mass spec binning, because with high-res instruments, one injection to the other, you could be a part or per million off, and your mass to charge, that could be enough to throw your statistical analysis off. So by binning, you kind of pick a mass to charge window that you allow those ions to be in and call it sort of the same thing. Confirm extraction of adulterant spikes. So they actually had to do the target analysis too to make sure, yeah, our method's working. So if we go through all the rest, this statistic analysis, we're not wasting our time. ProFinder, and this is interesting. I don't know if anyone else has ProFinder here, but this is sort of Agilent's newest software. And rather than having you look at each chromatogram and sort of look at the ions manually, it will look at the whole data set sort of globally and say, these are good ions, these are good features, and they call it batch recursive feature extraction. And one thing it does is eliminates one-hit wonders, like if you have these 5 replicates and here's a nice ion, but it's only in one of the replicates, do you really want to look at it and be comparing it to all of the others? So you got to choose how many of your reps have that feature, and it's a quality feature. And so finally, after you have your data set with your samples and your features, you can go to Mass Profiler Professional. Anyone have Mass Profiler Professional? This is their Agilent's $15,000 statistical chemometrics package. So.
Come on to offer ProFinder.
ProFinder?
Yeah, using your PID coded array called PID.
See,
ProFinder.
ProFinder.
Software we offer some other offer.
Oh, you have the same, yeah, because I think all of the big companies have something similar now. Thermo has Compound Discover, I think it's similar, okay. And what's interesting is just doing the PCA based on a huge number of features, 6,000 or 7,000 features, without much feature selection. Again, it's probably hard to see. The blue is spiked and the red is the control. You don't really see a lot of separation there between the, on the far left is all of the spikes versus the control. They're kind of all jumbled together and not much different than just looking at PCA of all of the unadulterated lots. So feature selection is important. And they went on, the question is, can the features be found? So there's the compounds. I believe that's ricinin on top, colchicine, oxycodone, and yohimbine, if I remember that right. So what they do next is the software allows you to look at the features in your suspect sample versus your good model, and you can apply filtering tests to see what looks like it's higher, you know, a twofold difference in the suspect versus control. Let's just look at the features that are much more elevated in the suspect. Or let's just look at features found only in the suspect. And in case what they did here, they did that and then narrowed the retention time bin to down so they had only 20 features that were the highest quality features. And you have to read the paper, but they claim that they did identify all 4 compounds in 4 different databases using their the data filtering and their feature selection. Feature selection is really the name of the game. So I want to go into one more thing. This is the most interesting thing to me, really. This is the last example. This is from the Forensic Chemistry Center for FDA in Cincinnati, Ohio. So they're part, I don't know if anyone's from Cincinnati here, been here. I have been there. It's really an amazing lab. And so they're part of ORA. So these people do the criminal investigations. They can work with the Justice Department to have people arrested and thrown in jail. And that's the kind of example we'll look at here. This is pure chromatography here, no high resolution mass spec. So the FDA, the Forensic Chemistry Center, they support regulatory investigations, criminal investigations, work with all kinds of products, not just food, drugs, supplements, cosmetics, whatever. And research, develop new methods to support FDA investigations. So this is a dietary supplement example. FDA investigators suspected some ingredients were adulterated. And the samples in this case were chasteberry extract and milk thistle seed powder. I had never heard of chasteberries. Anyone in here heard of chasteberry? And I read up a little bit about it. Evidently, it's a berry medieval monks took to quench certain desires in them. And I was amazed. I guess people still buy it and take it. So milk thistle seed, I don't know anything about that, what that's used for anyway. But so anyhow, they got samples from the field. It's called a field investigation. And they didn't get any control samples, so they had to sort of they got their own. And the first thing they did here is light stereo microscope investigation. So comparing maltodextrin to the chasteberry powder. So on the top left is the suspect's chasteberry. On the top right is maltodextrin, a little bit suspiciously looking alike. And then on the bottom left, the pure stuff, the bottom right, the pure chasteberry powder. So you can look at that, yeah, it might be adulterated. But they went on and did some chromatography on this. So the dextrin, maltodextrin are starches, polysaccharide, partial hydrolysis of starch, glucose units. I don't want to go into all the chemistry, but basically they're a type of starch, the maltodextrins. So looking at a real chromatogram here, this is Carbopec 200 with a sodium acetate eluent potential, let's see, pulsed amperometric detection. I used to do electrochemistry, it's been so long I almost forgot, which is used frequently, I guess, for sugar. So there's your maltodextrin. Here's the profile of a control, chasteberry in the middle, the suspect on the top, maltodextrin on the bottom. So it's pretty obvious that there's some adulteration going on. And they also decided to hydrolyze the samples to look at the glucose content and calculate the maltodextrin. And if you look at the suspect samples, they're over 90% maltodextrin. And I guess the upshot of this, somebody did go to jail for that. So that's the kind of interesting stuff that the ORA does. So yes. And you know, this is not just a one-shot deal. This goes on, I think, pretty frequently. So I'd just like to finish up and acknowledge people that have helped me with this presentation. My boss, Lauren Jackson, and Ann from CFSAN in College Park. Catherine Dassenbrock is from the Cincinnati Forensic Center. Zhenfeng Wang, the postdoc that did the lemon juice work, and then Jeff and Jim that helped me with the skim milk powder. I learned my chemometrics a lot from those guys. And just say thank you for listening and showing up. I'm honored to be here. And I'm done. And if there's any questions, I'll take questions.